Shall we start now? Hello and welcome to today's SIGSOFT webinar. This webcast is part of SIGSOFT commitment to provide value to its current and future members. The webinar series features speakers from the Future of the Software Engineering track at the International Conference of Software Engineering, as well as select keynote speakers and distinguished paper award. I am Xin Hu from Zhejiang University, and I'm the assistant professor. And it's my pleasure to welcome you today. Before we get started, I'd like to quickly mention a few housekeeping items shown on the slide in front of you. If you have any questions during this webinar, please type them into the Q&A box at any time. At the end of the presentation, we will have time to respond to the questions. This session is being recorded and will be archived. You will receive an automatic email notification when it becomes available. Today's presentation is from SBOM to Trustworthy Software Supply Chain, How Far Away? By Xin Xia. Dr. Xia is the director and scientist of the Software Engineering Application Technology Lab at Huawei, China. His research interests include intelligent software engineering, mining software repositories, and empirical software engineering. Dr. Xia has published more than 270 papers with a Google Scholar citation more than 10,000. Dr. Xia won the SIGSOFT Early Career Researcher Award in 2022, and some of his papers won the Best or Distinguished Paper Awards from various software engineering conferences. Let's welcome Dr. Xia to start his talk.
Okay, thanks, Xin. So, good morning, good afternoon, and good evening, everyone. So, welcome to attend my talk. So, today I would like to present some of our research progress on trustworthy software supply chain. So I'm Xin Xia. I'm currently working at the Software Engineering Application Technology Lab, Huawei, China. So when we mentioned the software supply chain, so we normally will begin with the with SBOM. So SBOM, which means the software bill of materials, it is originated from the global challenges to software supply chain security and transparency. So it has about 80 years history. For example, in the year of 2014, so the US proposed the Cyber Supply Chain Management and Transparency Act, so requiring all the government agencies to obtain SBOMs for any new products they purchase. So that is to say, for example, if a government agency wanted to buy Microsoft Office, so they will require the Microsoft Office to attach the SBOM, which records all of the third-party libraries or the open source components they used. And but however, at that time the act was not passed. But at the year of 2018 and 2019, actually the NTIA, that is National Telecommunications and Information Administration, and NIST, the National Institute of Standards and Technology, so they all proposed the idea of the SBOM to improve the transparency of software supply chain. So for example, in 2019, the Dr. Alan Friedman, so from NTIA, give a keynote mentioning the transparency in the software supply chain, making SBOM a reality. So they called more organizations to participate in this work. So this is something happened in 2019, but in 2021, so actually the White House officially issued a presidential order which requiring the software supply chain to provide SBOM for review. So at the time, we think in the future, so when we want to release our software products, we need to attach the SBOM to record all the components we used. So now the question you may ask is, what is SBOM? So what is SBOM different from others? So in general, the idea for SBOM is not difficult. It is as as recorded in the official website. So SBOM actually is a list of ingredients that make up the software components. So here I would like to give you an example. So suppose you develop this application, Acme's application version 1.1. So for the SBOM for this Acme's application, you will record the dependencies in this application. So if you check the SBOM, and you can find it depends on the Bingo's buffer version 2.2 and the Bob's browser version 2.1. So in this case, these three can composes the SBOM of Acme's application. And then if you want to check the software components used in Bob's browser, so you can check Bob's browser SBOM. So you can find it depends on the Caro's compression engine. So in this case, when we check the SBOMs for different components recursively, so you can form this kind of dependency graph. So in general, there would be 7 core elements of SBOM, and these 7 core elements can be extended. So these 7 include, for example, the component names. So as this example is Acme's application, and the supplies name. So who published the SBOM, and the version strings like the version 1.1, the author, the main developer who created the SBOM, and the hash to build the mapping between the SBOM to the application. And this is the unique ID which uniquely defines this application. That is to say, this ID cannot be changed. If the application is changed, the ID will change it accordingly. And also the last thing, also the most important thing, is the relationship. So that is the dependency or the third-party libraries or the open source components they use. So all of these 7 elements form the SBOM. And also SBOM now becomes has a lot of ecosystems. So from globally, there are 3 standards for SBOMs, which is funded by different international organizations. For example, SPDX is funded by Linux Foundation. SWID is funded by ISO and ICC, and it is widely used in the NVD, the National Vulnerability Database. And the Cyclone DX is funded by OWASP, and all of these standards has published a lot of tools to generate SBOM automatically. And these standards can use in different scenarios. For example, for the compliance, for the vulnerability tracing, for the software identification, and many others. So actually, in terms of SBOM, there are lots of challenges. Actually, the first challenge is how to generate the SBOM automatically. So to solve the problem, so inside Huawei, we developed a tool named SBOM generation framework, which can integrate all of different kinds of SBOM generation tools and output the SBOMs which follows the Huawei standards. So there are many challenges. The first is, for example, when we want something to be practical in industry, so we need to consider different programming language like C, C++, Java, Python, Rust, and many others. But for C and C++, the dependency analysis is not mature. So we need to develop our own technology to generate the SBOM for C++ programming language. And also for some of technology, we need to generate SBOM under the building process. So, but as in a bigger company, the building environments can be very difficult. For example, there would be multiple building systems, and also there would be different building project implementation and multiple programming language and multiple package manager. So all this cause a lot of challenges to generate the SBOM automatically. So to solve this problem, actually, we consider the software production pipeline. For example, when we have the source code and we can build the source code. After the building, we can get the package, the binary package. So actually, the SBOM generation technology should consider both of these 3 user scenarios. So then we divide the SBOM generation technology based on these 3 these artifacts. So for the source code level, so we can use we developed our architecture reverse engineering to generate the dependency for different source code. For example, for different classes, so we can build the dependency to identify whether class A is dependent on class B, and whether there are some dependency, like dynamic dependency. And another technology is clone detection technology, which you can use to, for example, we can use the source code of OpenSSL to detect whether our source code used OpenSSL. So this is one part we are developing now. And the second thing is in the building phase. So we can use, especially for C and C++ program language, so we can use building to extract dependency to generate SBOM. And also for some programming language, so they provide a very good package manager like MemVul, Cargo, and NPM. So we directly use the package manager to generate the SBOM. And actually, the most difficult thing is for the binary package. So if we don't know anything about the binary package, so we also need to use the software composition analysis technology to generate the SBOM from the binary package. And also we need to use the binary to validate whether the SBOM we generated all the open source components we identified really exist in the binary code. So this is some challenges, and actually the most difficult part is we need more advanced progress in the software composition analysis. So this is the overall situation of SBOM. So before I present how SBOM can help improve the transparency of software supply chain. So let us go back to talk about the challenges when we meet for the software supply chain. So here, this is I use the Log4j vulnerability appeared in last December as an example to show the severe challenges we meet for the vulnerability management. So actually, in last year, so some developers at Alibaba found that some functions of Apache Log4j has recursive passing function, so that the attackers can construct a malicious request to track to trigger the remote code execution. So it's a kind of nuclear vulnerability because you can remotely execute the code in another server. And also after it is published, disclosed in December 11th. So in 3 days, a lot of they received the hackers launched more than 830,000 attacks. So this is a lot of attacks for the Log4j vulnerability. And actually inside Huawei, we also discuss a lot about this vulnerability. Actually, this is the whole history about the vulnerability. So actually it is discovered in November the 24th. At the time, Alibaba notified the Apache community of the vulnerability. And the community discussed the issue on December the 2019. And also Alibaba Cloud closed the vulnerability on December the 9th, and then Huawei found it and Huawei registered the vulnerability in our vulnerability management system. And in December the 10th, so it is officially announced by the NVD. And after that, actually Huawei spent a long time actually to try to identify which products is affected by the Log4j vulnerabilities, and then we spent a lot of time to try to fix the vulnerability and provide the patch. So this is the whole progress for the Log4j vulnerability and the steps we are doing inside Huawei. And after that, actually we find that we need to have 3 capabilities to improve our vulnerability management. The first thing is you can notice that the vulnerability is reported on November the 24th, but it is only disclosed in December the 9th. So that is to say there is a silent period for this vulnerability. So whether we can mine the open discussions or the commits for the open source communities to early identify or early awareness of the high risk vulnerability, this is the first thing we would like to build. And the second thing is once we have the vulnerability public disclosed, so the second thing is which products or which components is affected by the vulnerability. So we need to provide the accurate demand accuracy and assessment of the high risk vulnerability. So in this case, actually SBOM can help a lot. Suppose all of the products provided the SBOM, so then give any vulnerabilities and it's affected the open source components. So we can use the SBOM to query which product is affected by the vulnerability. And the second thing is, even we spend a lot of time trying to fix the vulnerability, still we find a lot of communities did not fix it. Because, for example, in the January, the end of January, we still find that certain versions of the communities from Huawei did not fix the vulnerability. So we actually needed the capability which can provide the remediation of the high risk vulnerability with days. For example, whether we can fix it in 1 day or 2 days. So this also raises some challenges or the technical challenges. And also, besides the vulnerabilities, actually, from the software supply chain, there are lots of poisoning attacks. So here are some example, one example. So there are some, for example, you can, this is the package, the PyTZ package, which provides a mapping table of time zones in different countries. And actually, some developers create a new version named PyTZ 3 dev. So they create this package from the PyTZ, and they added some malicious code, and then they release this again. So then a lot of people download it. It costs a lot of attacks from the supply chain. So this is one example we find. So there's some confusion between the names of a malicious package and the valid package. And also, according to the Sonatypes reports, they find from 2020 to 2021, there is an increase of 650% increase of attacks for the open source software. So this also raised a lot of challenges, especially to the poisoning attacks. So we needed to have our capability to prevent this kind of poisoning attacks. And also, so this one, so I'll try to answer the question. So what is how to from SBOM and to the trustworthy software supply chain? So actually, SBOM, you can think it's the data foundation of the whole software supply chain, and especially it can help to improve the supply chain transparency and end-to-end vulnerability tracing. However, so when we work at the whole trustworthy software supply chain, we need more capabilities. For example, we needed the capability for the early awareness of vulnerabilities, and we need some technology to do the vulnerability discovery and scanning. And also we needed to have the capability for the poisoning awareness. So all of these kind of capabilities cannot be built based on the SBOM. So in this case, so we will provide our preliminary thoughts about the trustworthy software supply chain solution. So in total, there would be 6 sub-solutions, as I mentioned. So the first one is the vulnerability awareness. So it can be divided into 2 kinds of vulnerability awareness. One is whether the vulnerability is public disclosed, whether we can detect it. So for example, if it is discussed the vulnerability in Twitter, in NVD, and in other websites, whether we can identify this kind of vulnerability information. And the second thing is whether we can perform the early identification of the silent vulnerability fix. For example, whether we can identify whether an issue report in GitHub will become a vulnerability report, whether a commit in the GitHub is relevant to the vulnerability fix. So this is the first thing. And the second thing is vulnerability discovery and scanning. So in this case, we would like to use the fuzzing technology to detect the vulnerability or mine the open source project to identify the vulnerability. And another thing is we can use the clone detection. For example, use the historical vulnerabilities to detect whether the similar vulnerability exists in the open source project. And the third solution is poisoning awareness. So that here to say whether we can have build a system to, for example, monitor the healthy, whether the open source community is healthy, whether the code developers submit to the GitHub is malicious, or whether we can detect some suspicious people who do some suspicious behaviors to the open source software. And the fourth is the end-to-end vulnerability tracing. So in this case, actually, SBOM can help a lot. So we can use SBOM to notify the developers which products or components is affected by the vulnerability. And the key technology is the software composition analysis. And the fifth solution is the fast vulnerability remediation, whether we can repair the vulnerability automatically. So this requires a lot of research progress, especially for the program repair. And the last one is the software supply chain security risk control. So in this case, even the vulnerability or the poisoning behavior happens, whether we can prevent it by design some systems. So this is the six sub solutions we think which is important for the trustworthy software supply chain. So due to time limitation, so I will quickly introduce some of our research progress in the vulnerability and the poisoning awareness. So this is some of progress our progress on vulnerability management. So actually, if you check the security vulnerability disclosure models in the industry, actually they have three kinds of model. The first one is the full disclosure model. That is to say, once there is a vulnerability discovered in open source community, so we will report it, we will put it public. So in this case, both the users or the hackers will get the information at the same time. So in this case, if the hackers have small capabilities, so they can directly attack the system. And the second model is no disclosure model. That is to say, no information about vulnerability is disclosed. So in this case, no one knows the existing of the vulnerability. And the third model is the coordinated vulnerability disclosure model. So this is actually the widely used one. So in the coordinated vulnerability disclosure model, so the vulnerability is only disclosed to public after a period of time, so that it can be patched or fixed. So this is the commonly widely used model. And so here we would like to check the whole coordinated disclosure model. So suppose there is a vulnerability discovered in an open source project. So it is discovered, confirmed, and then developers will try to fix it. And then the fixing patch is integrated into the new version. And then it is put into the security vulnerability disclosure platform such as MVD. And at that time, actually, some companies like Huawei will notify it there is a vulnerability, and they will try to fix it. Actually, for the step 1 and step 3, you can find that there is a time gap. For example, for step 1, so this is the example which is an issue report in a GitHub project. So it is published in March 24th, but only in October 5th it is said that this issue is corresponding to a vulnerability. Actually, there are almost half a year gap for this issue report and for the public disclosure of this vulnerability. And this is another example. So actually, this commit is put into the GitHub repository on January 24th, but only in November 5th. So it is published, announced that this commit is fixed this vulnerability. Actually, this is almost a 1 year gap. So actually, if I'm a hacker and I'm very strong in analyze the open source data, so I can use the leaked information to launch the end-day attacks. So to solve this problem, so inside Huawei, so actually we try to build the capability to discover whether the issue reports will become a vulnerability, and whether the commits will become a vulnerability patch in the future. So this is two things we are doing for the earlier awareness of security vulnerability detection. And also, besides the early awareness, we also find actually CVE has a lot of issues. For example, there is unreliable vulnerability version information. So when you check the CVE, because it did not provide whether the version affected by the vulnerability is verified. So in this case, the version, many of the version number is not correct. So here is an example. We use the CVE 2018-662 as example. So you can find it is changed twice. In the beginning, it said the version affected is 3.4.1, but later it changed to 3.2, version 3.2. But when we manually check the affected version, we find it is still not correct. We find it the range is 3.1 to 3.2 and 3.3 and 3.4. All these versions is affected. So in this case, the version is identified by the reported by the CVE might have some problems. So we need some technology to automatically identify the versions. And also, even the version is correct, the second challenge is we need to locate the vulnerability components. So for example, inside Huawei Yun, actually all of the products will use Spring. So once we tell the Huawei Yun developers that our vulnerability affects the Spring product, affect the Spring, so it is meaningless because they need to check all of its products to identify whether the vulnerability is affected by the product is affected by the vulnerability. So in this case, they want to more fine-grained level. For example, whether we can tell them the vulnerability only affects the Spring Core or Spring Root or other packages. So in this case, they can narrow their search space to identify the vulnerable components. And also the last thing is we noticed some of the vulnerability fixing patches are missing. So this is the example from the Android open source project. So we find most of the vulnerability for the AOSP is vulnerability fixing patch for the AOSP is missing. About 6 of them is not available. So we need to choose some technology to link the vulnerability description to the vulnerability fixing patch so that developers can easily put the patch into the productions and others. So this is all the challenges we meet. So to solve this problem, especially for the early awareness of the critical vulnerabilities in ICSIS next year, so we propose that technology based on the constructive learning. So the main idea is we divided the patches on GitHub into 2 types. One is the vulnerability fixing patch, another is the other types. So we use the constructive learning to try to learn the difference between the vulnerability fixed patch and the non-vulnerability fixed patch. And then based on it, we build the BERT model, and then we use the model and fine tune it and to fix to solve 3 problems. The first one is we will tell developers given a vulnerability whether it is a vulnerability give a commits whether it is a vulnerability fix commits, and then if it is a vulnerability fixing commits, we will tell them their CVE type. So we find actually some CWE type has a high risk to be critical vulnerabilities. And the third thing is we also computed the CVEs score. CVEs score, you can think it's more like the to measure how serious the vulnerability is. So if it is above 9, we can think it's like the critical vulnerability. So this is our framework, and also we use this technology to detect the real vulnerabilities in practice. So we actually found first of all we find our technology outperform the state of the art a lot, and also when we use it in the Apache projects from September to December. Actually, we find there are 3 high-risk silent vulnerability, and among the 12 high-risk vulnerability fixed, we confirmed there are 2 critical silent vulnerability fixed, and also we have also identified 3 high suspicious vulnerability fixed. And also we apply our technology in AOSP. We also discovered 29 high risk of silent fix, and among them 8 are critical fix. So this shows that this kind of technology can work very well into the industrial environment and can really help to detect the critical vulnerability. And the second thing is we also wanted to identify the issue reports, which will become the vulnerability reports. So we also developed the model which is based on the Siemens neural network. As you may know, so for the issue, there are only about less than 0.35% of the issue reports which becomes the vulnerability reports. So it's like the find the needle in a sea. So in this case, we build the model to consider the class imbalance situation. So the main idea is given an issue report in GitHub, so we measure the similarity between the issue reports to the CWE categories, and then based on it, we build the Siemens neural network to measure the similarity for issue report to CWE category, and then the outputting the scores, and then we try to classify each issue report is whether issue report will become a vulnerability report or not. So in this case, actually, you can find that although the performance of every score is less than 0.5, but this is the first step, and when we put into practice, it can among the 5 issue report we tell the developers there are 2 or 3 is identified as the vulnerability report, and this is also integrated into our internal platform to identify the vulnerability relevant issue reports. And we also propose a clone detection technology to detect the similar vulnerability. So the main idea is giving a vulnerability in code. So we use the clone detection to detect whether there would be some similar vulnerability exists in the product. So in this case, actually, we find most of the deep learning technology cannot work very well to solve this problem, because deep learning, some technology sometimes worked very slow, and they identify a lot of type 4 clones, but it is hard for developers to validate. So in our case, actually, we propose a simple but fast and it will require less people involvement technology to solve the problem. So the main idea is to give a piece of code. So we divide it into n-gram. For example, this is 3 gram. For the 3 gram, we then use the hash to mapping this 3 gram to the hash value, and then we integrate this whole hash value into one final hash signature for the code, and we use this fingerprint to measure the similarity between 2 pieces of code. And in this case, it's very fast, and it can detect the type 1 and type 2 clones and some of the type 3 clones. But when you want something to be used in industry, focus on type 1 or type 2. In the beginning is enough, because it's easy for developers to identify whether the 2 pieces of code are really similar, so this can easier to identify the similar vulnerability. So in this case, actually, we also identify them, for example, certain suspected vulnerability code snippets in the Linux kernel 5.1, and we report to the developers in the community and try to fix them. And also to correct the version of the vulnerabilities, we propose that our own vulnerability assay algorithms, so different from the traditional assay algorithms, which mostly identify the first commits that introduce the bug, but for the vulnerability, we need to choose much far from the first commits we identified. We need to choose from the beginning of the project to identify the first version which introduced the vulnerability. So this is something different from traditional assay algorithm. So we develop our own vulnerability assay algorithm. So for more details, you can refer to our paper. So based on our vulnerability assay algorithm, you can find it can identify the version ranges very accurate. So the precision and the recall is almost 1. So it improves a lot for the existing assay algorithm. And also for the fixed pattern identification, so we also propose a technology which mentioned given a vulnerability and code commits. So we measure the similarity between them, and we build the deep learning model to mapping these 2 into the deep learning features. And also we extract the other features, for example, the lines of code in the commits, the identity features and the location features and the token features. Then we put all the features together. We build the model, for example, to do the one to identify whether the code commit is the vulnerability fixing patch. So provide this kind of classifiers. So in general, actually, when you check the record, especially for record 1, it is almost 0.9. So we think it can really help to detect the patches which fix the vulnerability. So this is the progress. And also the last thing is we also to try to locate the components, the fine-grained components in the vulnerability. So we will build the NLP-based technology. So here is an example. So this is the vulnerability described in the NVD. So we use the NLP technology to analyze each sentence in the CVE, and we try to map each phases into different categories, like the vulnerable products, vulnerable version, the vulnerable component type, root cause, and others. And then we can extract mapping the descriptions into this field, and then we can identify the vulnerable components. So the main difficulty here is we need to build our own name entity recognition technology, which is also a deep learning based technology. So for more detail, you can refer to our paper. So this is some progress on the vulnerability management, and also in the following times I will present some of our progress on the poisoning prevention. So the first thing is we try to analyze what kinds of poisoning attacks may exist in the software supply chain. And this is a paper from the Auckland conference. So in total, there are 3 categories. The first thing is developers may create a malicious package from scratch. Actually, in this case, it's harder to detect it. And the second category is create name confusion with the legitimate package. So that is to say they give a package, they create a vulnerable package which has a very similar name to the legitimate package. And the third way is to subvert the legitimate package. For example, they inject some malicious code into the package, and they can inject the malicious code during the build of the package, and also they distribute the versions of legitimate package to different places. So all of this can correspond more than 20 plus vulnerability attack behaviors. So actually inside Huawei, we are trying to build all the capabilities to prevent this kind of attacks. So some is based on the name convention, confusion identification. Some is based on program analysis. For example, we try to analyze the code, whether the code contains some malicious behavior, and some we need to improve our building system to ensure the building source and the building process is trustworthiness, and some need to monitor the open source community to detect whether the community is healthy or not, or whether there are some malicious behaviors from the developers. So based on it, actually, the first thing we're doing is for the package name confusion detection. So actually, so we giving a package. So we first extract a lot of metadata. For example, the package name, version release time, dependency, package, and many others. And then based on the metadata, we build a model which measures the similarity of the package we have to the package in the block list, or the package in our database to measure similarity. For example, the dependency similarity, open source similarity, developer similarity, and the package name similarity. And then we extract some suspicious packages, and then we perform more fine-grained analysis. For example, use the security rule to detect the model, whether the model, the package contains some malicious code, and many others. Then finally, we can solve the package names spoofing and provide package confusion alarms to the developers. So actually, in this case, we detect a lot of the name confusion cases inside Huawei. So now it is put into practice. And the second thing is community monitoring. So this is some of our ongoing the ongoing work of our team. So the main idea is we monitor the open source community. We mine each commit, mine the discussions, and mine the issue reports, and we try to extract a lot of features, and based on this kind of features, we try to build the model to predict whether a commit behavior is malicious or not, and whether the overall healthiness situation of the community is good or not. So, for example, suppose it's core developers, the core contributor suddenly leave the community, and also for example, the community has a lot of newcomers, and they submit a lot. So maybe there are some risk for the open source community. So in this case, we can give the warning to the developers, and then we can provide more fine-grained analysis to the community. And also, this is some of our current progress. Actually, we also meet a lot of challenges. Actually, the first challenge is, as I mentioned before, the early detection of the critical vulnerability fix, early detection of the critical the high risk of vulnerability. So although we have some technologies, we still want to have more advanced technologies to solve the problem, because now we find actually only less than 0.35% of the commits are vulnerability patch. So it's very hard to detect this kind of patch. So we want the high accuracy technology, and also we also needed some automated severity evaluation algorithm that you see, especially in industry. So when you detect a normal vulnerability, it's create limited values. So, but if you can detect the nuclear level or the critical vulnerability, it creates a lot of value, because you can inform all the products to fix the vulnerability before it is published, disclosed. So that here to say we needed the automated severity evaluation algorithms for the open source software vulnerability detection. And the second thing is we need some more technology for the binary vulnerability scanning. So currently, the binary code analysis is very challenging, because once the source code is compiled to the binary for different compiling environments, the binary code is different. So the first thing is we really want the binary file conversion technology, that is to say convert any binaries which is built under different platforms into the unified intermediate code representation. And also the second thing is we wanted to check whether the similar vulnerability exists or not exist in the binary, because we find the code before and after fix the vulnerability may be very similar, and especially in the binary, it is really hard to detect whether a vulnerability is fixed or not fixed in its package. So we need some more advanced binary similarity vulnerability detection technology to solve the problem. And the third challenge is we really wanted to have the effective malicious code identification. So as I mentioned before, there are about more than 20 plus ways for the poisoning attacks, and most of the technology will require lots of program analysis. So we needed to, for example, to improve the current the performance detection performance for the current malicious code identification, and provide more, for example, support more programming language, support more programming language, and support that can automatically identify more patterns to solve this problem. And the last challenge is we wanted to monitor, because we wanted to monitor the open source community. So we really wanted to identification in the suspicious persons based on his behaviors. So in this case, we need to model them. What is the suspicious community behavior, and what is the suspicious community members? And this is some of our idea, but it's hard to put into practice because it's hard to evaluate whether one behavior is malicious or not. So this is something we really wanted to work with you to solve the problem. And for the future directions, so as I mentioned today, I talked a lot about SBOM and the trustworthy software supply chain. So in the future, actually, you can think this is a part of the software asset management. Because now SBOM is, you can think it's evaluate the results of the software artifacts, but for the process of the software development, it is not recorded or monitored. So the first thing is we can think is how to generate the metadata for the software development process. For example, whether we can record from which time and who did what kind of actions to the software system. So this kind of things should be recorded. So in this case, we can analyze whether his behavior is malicious or not, and then we can provide the end-to-end evidence to show whether the system is under production. And the second thing is the code asset management. It is like whether we can detect the technical debt, and we provide some technology to improve the quality of the code and to make the code to be the high value asset inside the company. So this can be the next step, and we are trying to still on the way to solve these problems. So this is all of my talk today. So thanks for attending this SIGSOFT webinar. Thank you.
Thank you, Dr. Xia. Thanks for your nice talk. Let's move on to the questions and answers. Our first question is, what are the major challenges in software composition analysis, including source code and binary?
Okay, let me. Okay, so there are many challenges. The first challenge is for the binary code. So in theory, one capability we were thinking is giving any binary, whether you can tell us what kind of open source component they use. So in this case, the main challenge is we need to build a very large, you can think of the knowledge database which contains all the binaries from open source communities, and then we can use the binary similarity technology to identify whether the binary exists in the binary package you provided. So this is the challenge, and also we need to design the similarity measurement algorithms very carefully, because sometimes for among the different versions, maybe the code changes is limited. So in this case, how to detect how to detect the versions from the binary, and also for the source code level, because sometimes there are some hidden dependency inside the source code. For example, some dependency only appears when we run the software. So in this case, how to use the static analysis technology to detect this kind of dependency. This is also very challenging. And also another thing is about C and C++. So it's different from Java or Python, which we can recompile the package into the source code. For C++, it's hard to recompile it to get some source code. So in this case, we need some other ways to measure the similarity between the open source components and also the binary code. So this is also very challenging. So all of this pose a lot of challenges, and also when you consider more programming language and more user scenarios, it will have some more cases for the difficulty for the software composition analysis.
Thank you, Dr. Xia. And the next question is from William. I can understand how code using external references can help develop an SBOM. What about code that uses call by value rather than call by name? No external references, only a raw address.
Code.
Call by value. Yes.
So sorry, I'm not quite understand this question. So what is call by value? Okay, so I guess maybe you ask whether the dependency is dynamic or static, right? So if it is the static dependency, I think it's more So actually, currently the SBOM wanted to generate the dependencies. Actually, the dependent you can think mostly it's like the dependency for product A and the product B. It's like the most like the static dependency. It's for the dynamic one and dynamic dependency, which you, for example, the runtime dependency. It's currently it is hard to build the SBOM. So this is some new technology we would like to build in the future. For example, in terms of for the microservice, so I think all the code is called by the dynamic the dependency is built dynamically. So in this case, how to generate the SBOM for the microservice is also a new problem, but it is not solved yet. So we can explore it in the future, I think.
Okay, thank you. And there is also a question for SBOM. I also have some questions regarding SBOM. In daily software development, is expect for directly including the open source software as dependencies. It is also common to reuse some code snippets, for example, just a piece of function from the open source software. Is SBOM capable of covering such fine-grained software artifacts?
Okay, this is a good question. It is possible to record the file level to generate a file level SBOM. So for example, if you copy the code from the open source project and you use it in your project, it can be recorded, and the key technology is the clone detection technology. But when we mention it to the software asset management, if we focus on this fine-grained SBOM, it will cause a lot of difficulty to manage the software assets, because if you manage we think the software asset management level should be the component level, not the file level. But the question is, in the future, it is possible for the SBOM to generate the file level information. For example, whether a piece of code is copied from an open source project. So this is possible.
Okay. Some existing works show that it is possible to employ clone detection technologies to conduct zero-day attacks by finding similar vulnerable code snippets based on the known vulnerabilities. How can we deal with the security risks caused by such hidden dependencies in software supply chain?
Actually, so when you use the clone detection to detect the similar vulnerability code, and so hidden dependency. Okay, so I think one simplest way is, for example, we build a very large vulnerability code snippets, and we use this as the code base to scan all of the open source projects and to identify whether there is a code snippet is similar to the code snippets in the similar code snippets in the vulnerability code base we have, and if we find that there are some similar vulnerabilities, we can report it, for example, to the community, and in this case, this kind of vulnerability can be fixed. And also, we can develop another technology to automatically generate the patches to fix the vulnerability we detect.
Thank you. And there is a question about the vulnerability and the bug reports. I have a question that CVE or bug reports are the description of the vulnerability in natural language, and the vulnerability is that the code is different from natural language. There is a semantic differences between the code and the natural language. How to shorten the meaning differences between them?
Okay, so that's a good question. So So the description in the CVE and the code can be very different. So in this case, we need to build the joint embedding model to mapping this the code and the CV description into a you can think it's a high dimension space, which this kind of the semantic gapping is addressed. So this is the main idea, and you can use like the for example the word embedding or some code embedding technology to solve the problem. So this is the things. And another thing is that we can directly use the NLP technology, for example, to analyze each sentence in the CVE and each code snippet, each statement in the code, and we can try to build this kind of mapping into to identify some similarity between the code and the CV description.
Thank you. A question from Christina asked: Are the different ways to generate a SBOM compatible with each other or use a common standard? If not, is there work other way to create a common framework?
So sorry, can you say again?
Are there different ways to generate a SBOM compatible with each other or use a common standard? If not, is there work other way to create a common framework?
Okay. So this is a good question. So now, as I mentioned, there are a lot of SBOM standards. For example, SPDX, SWID, and Cyclone DX. They all have its SBOM standards. And also inside Huawei, we also have our own SBOM standards. Although most of the field is similar, but there are some field are different. So in this case, we need a framework to should be adapted to different kinds of SBOM standards. And also, although they provide some SBOM generation technologies, but if you use this kind of tools, you can find that even for Java, the SBOM generated the dependency generated by SPDX and the Cyclone DX may be different. So actually, in this case, we need some more unified framework which can integrate all of these tools and select the best tools to generate the SBOM for different kind of programming language. So that is why we need this kind of framework. And we also noticed that Microsoft also published some similar SBOM generation framework and to deal with the same questions we met.
Thank you. And there are also some questions to ask that, are you making your slide deck available anywhere?
Yeah. So we will make the slide deck available.
Okay, I'm afraid we have run out of time today. I'd like to thank Dr. Xia again for the informative representation and insightful answers to many questions. Special thanks to each of you for taking the time to attend and participate in our today's webinar. This webinar was recorded and will be available online in a few days. On behalf of SIGSOFT, the speakers and myself, thank you again for joining us, and I hope you will join us again in the future. This concludes today's webinar. Thank you.
Thank you. Bye-bye.
Bye.